Okay, so we are going to start the fourth section of chapter 2, which is solving absolute value equations and inequalities. So when we're done with this section, we're going to have to be able to solve absolute value equations as well as the inequalities and know how they work. As far as the equations go, I think for the most part, we're going to have quite a bit of success with this. Although there are some things that we're going to have to try to keep straight when we come to the inequalities, because it could easily be confused with one method or another. Okay, so let's go ahead and start. So one learning target, obviously, which is exactly what I've explained, which would be solving absolute value equations as well as inequalities. Okay, so as I'm looking at this, I'm going to try to walk us through the first one relatively slow and allow us to understand why these problems are going to work the way they are. So we need to understand some things about absolute value. Absolute value is quite literally how far a number is away from 0. So, for example, if I use the number 10, I want the absolute value of 10, you would ask, how far is 10 away from 0? Well, that question seems kind of obvious, almost trivial, that 10 is just 10 units away from 0. But as I think about that, is 10 the only number that is exactly 10 units away from 0? So I want you to, and if you have to, pause the video and think about this. Like, what other number is also 10 units away from 0 exactly? So hopefully you've thought about this a little bit and are telling yourself that, hey, there is another number. It's negative 10. So as you take absolute values of numbers, this inside part matters quite a bit, right? So regardless of whatever's on the inside here, we know that's going to end up being a positive number because the distance is like a positive thing, not really such thing as negative 5 feet. But regardless of whether this problem here, as I'm looking at it, if this inside part here is 9, when I take the absolute value of it, it's going to be 9. Similarly, for what I just talked about, since 9 is 9 units away from 0, negative 9 is also 9 units away from 0. So if this inside part here is negative 9, when I take the absolute value of it, it's going to be positive 9 as well. So we have to account for like both parts of this. So how are we going to do this? Essentially, we're just going to write two equations, and then we're going to solve them. Let's start with the most basic one. We know that if this inside part here, just the inside part, so 5 minus 2x is equal to 9. If we know that this inside part, 5 minus 2x, is equal to 9, then when I take the absolute value of it, it's going to be 9. Let's go ahead and try this out. So we can subtract 5. And after I subtract 5 from each side, I have the opposite, or negative 2x is equal to 4. And then when I divide by negative 2, I get x is equal to negative 2. Okay, so I get negative 2. Okay, so if I plug x in for negative 2, okay, I am going to get 9 on the inside. When I take the absolute value of 9, what do I get? I get 9. Let's go ahead and check our work and actually see that happen. So 5 minus 2 times negative 2 is equal to 9. Well, 5 minus negative 2, so negative 2 times negative 2 is 4, so 5 plus 4 is equal to 9. Okay, and then this is the absolute value of 9 is equal to 9, which indeed checks out. Okay, so that ended up working out. That's great. That's what we're looking for. But we also have to remember there's that whole other side. So we talked about, well, if that inside part's 9, absolute value of it's 9. Well, what about if that inside part is negative 9? What about if this inside part here, 5 minus 2x, is equal to negative 9? Because if this whole inside part here is equal to negative 9, and when I take the absolute value of it, it's going to become 9. So let's go ahead and solve this one. So I subtract 5 again, and I get negative 2x is equal to negative 14, and then divide by negative 2. So x is equal to positive 7. So we might as well go ahead and check our work. I'm just going to do it like right below here because I'm kind of running tight on space. Let's go ahead and make sure that that works. So we're going to say the absolute value of 5 minus 2 times 7 is equal to 9. Okay, so here I get 5 minus 14. Absolute value is equal to 9. So 5 minus 14 is negative 9. So I get the absolute value of negative 9 is equal to 9. What is the absolute value of negative 9? Same question as asking how far away is negative 9 from 0? Well, it's 9 units away. So 9 is equal to 9. So this checks out. This checks out here. This checks out here. So conceptually, what's happening is since absolute value is how far a number is from 0, there's a number to the right of 0 that is a certain distance away, and there's another number that's to the left of 0 that is the exact same distance away. Typically positive and negative of the exact same number, not typically always the exact same number. So that's why I'm taking this inside part, setting it equal to 9, and then this inside part and setting it equal to negative 9. Okay, if it just helps, you just set the inside equal to 9, the inside equal to the opposite of this number is 100% what is happening. Let's go ahead and see what the graph looks like. Okay, so the graph of my solutions, okay, because I do have 2 solutions, and I'm going to get, let's say this is negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7. Okay, just like all the other graphs that we've dealt with, I do want to see 0 and your critical numbers. They don't have to be units of 1 away. You can scale that however you want. Okay, so I'm going to put a bold dot here on negative 2 because it's equal to negative 2, and a bold dot here on 7 because it's equal to 7. Okay, now let's answer the question. We've kind of done a lot of shading in this chapter. Is there going to be any shading on this problem? Well, short answer, no. The reason why is there is no values in between. These are the only 2 numbers that are exactly 9 units away. So really you're only going to see shading when you have inequality signs, such as greater than, less than, greater than or equal to, less than or equal to. Okay, one thing that I will point out is although on number 1 I kind of checked my work to really make sure that this is how these answers were truly my answers, I'm not requiring that out of you. I would highly encourage it. I mean, you'll always have the tools to make sure that your answers are correct all the time by checking work, but I'm not going to require that. So feel free. Really, the only things I'm going to need to see is this, and your graph. Okay, now is a fantastic time to go ahead, pause the video, and try A on your own. All right, so I'm assuming that we've already tried A, and we're here just to see our work. So I know that if I'm taking the absolute value of 2x minus 7, and it's equal to 17, that means this inside part here, 2x minus 7, can be equal to 17. Okay, similarly, I also know that if I take that inside part, 2x minus 7, it can also be equal to negative 17, because these are the 2 numbers that are 17 units away from 0. Okay, and then I can just solve. Okay, so I add 7 to each side to get 2x is equal to 24. Divide by 2 to get x is equal to 12. Okay, and then this one here, I'm going to add 7 here. So I'm going to get 2x is equal to negative 10. And then divide by 2 to get x is equal to negative 5. Okay, so these are my 2 x values that are going to make this equation true. And so now I just need to see the graph. Okay, so let's just say that this here will be negative 5. Then this can be negative 4, negative 3, negative 2, negative 1, 0, 2, 4, 6, 8, 10, 12. Okay. And then these are my 2 answers. Again, your graph may look separate from or different from mine. Try to have it scaled appropriately. I'm going by 2's here, right? Negative 2, negative 4, negative 6, which means negative 5 would be in the middle. Okay, that's A. Again, the equation ones really aren't that difficult. You do just have to try to keep straight that the inside part can be equal to that positive value as well as that negative value. Okay, let's move on to problems like number 2. Okay, so as I'm looking at a problem like number 2, okay, there is a little bit of extra stuff going on, right? I have the absolute value of 3x minus 9, then I'm taking away 10 is equal to 14. Well, these problems could be solved quite easily if they were just set up like this. The absolute value of something is equal to a number. We know how to solve those. Those are very convenient for us to solve, especially if we have an understanding of absolute value. Well, this one's not quite in that shape, right? I have the absolute value of 3x minus 9, but then I'm subtracting this extra 10. So what we need to do is we need to kind of treat this whole absolute value symbol, okay, as if it was a variable. And we want to try to get the absolute value symbol isolated. So I'm going to put that down as a little note. Isolate the ABS. Okay, so ABS is going to stand short for absolute. So we want to isolate the absolute value. Okay, we want to get the absolute value part isolated totally by itself, and then we can just treat the problem as if it was a problem like 1 or A. So let's see what that looks like. So I have the absolute value of 3x minus 9. Then I'm going to take away 10. That's equal to 14. Okay, I just want to get this entire part here underlined in red. I just want to get that by itself. If I can get that by itself and have it equal to another number, I'm going to be able to easily graph this. So let's go ahead and think about it. What can I do? Just get rid of this 10 or this minus 10 so that this absolute value symbol is completely isolated by itself. Hopefully, as you're thinking to yourself at home or wherever you're watching this at, is that, well, if I just add 10, that will undo minusing 10, and you would be correct. So let's go ahead and add 10 to each side. So if I add 10, these parts cancel each other out completely. I'll even put a little cross through that. And now I get the absolute value of 3x minus 9 is equal to 24. Okay, so now this problem is set up the same way as above. Okay, and so knowing that we know how to write or solve the problems above, I'm going to go through this pretty quick. Okay, so the first equation we're going to set up is that the inside 3x minus 9 can be equal to positive 24. I also know that if I have that inside 3x minus 9, it can be also equal to negative 24. Because when I take the absolute value of 24, it'll be 24. And when I take the absolute value of negative 24, it will be 24. Okay, so I can add 9. 3x is equal to 33. 5 by 3. X is equal to 11. I can add 9 here to get 3x is equal to negative 24 plus 10. This would be negative 15. Okay. And then divide by 3. Okay, x is equal to negative 5. Okay, so those are our two values. And again, I'm kind of under the assumption that we've figured out how to do these types of problems based on the previous examples. The hardest part is just get the absolute value symbol isolated. Okay, so let's just call this here negative 5. Negative 4, negative 2, 0, 2, 4, 6, 8, 10, 12. So here can be 11. We'll die here. We'll die here. Okay, I would point out, I'm going to put this in blue, just a little extra note, because these notes probably should have something like this. What if I had like 2 times the absolute value of x plus 1 minus 4 is equal to 10. What if I had something like this? We're not going to solve this all the way. I'm just going to get us started. because I have like a number out here. This does mean multiplication, but we cannot distribute this. Okay, what I would want to do is I would want to add 4. Okay, and then after that I would have 2 times the absolute value of 2x plus 1 is equal to 14. Okay, you need to ask yourself, like, what would I do to like undo this 2 here? This means 2 times the absolute value, but there's not parentheses. There's nothing telling me that I can distribute this. So how can I undo multiplication? Hopefully we can all come to a little consensus here and say that we need to divide by 2. Those will cancel each other out. And then we can solve that our traditional way. So if you ever have a number out front of the absolute value, that does mean multiplication, and we would need to divide to be able to do that. Okay, great time to pause the video, try letter B on your own, check it with me here now. Okay, so I have this plus 4 here, so I need to go ahead and subtract 4. So I'm just going to subtract 4 up here. That'll get rid of that. That gets that absolute value symbol isolated for me. Okay, and so then I have here 3x plus 6 is equal to 0. Okay, well, the first thing I know is if this inside part here is equal to 0, then it's equal to 0. The thing about this particular problem, which this is a great problem, is that when it's set equal to 0, this is a situation where we're only going to get one answer. Because if this is equal to 0, that means the only number that's going to take the absolute value of to be 0 is 0 itself. So we only care if this inside part is equal to 0, because there's no such thing as like negative 0. 0 is neither negative or positive, it's just as it is. Okay, so we're going to subtract 6 and divide by 3. So x is equal to negative 2. Only one answer here, so we can just put 0 here. We can put negative 2 here. There's our answer. Okay. One thing that I think I want to add here, and again, I'm going to put this off in the side. What if I had the absolute value of x plus 1 is equal to negative 3? What would happen there? So let's just think about this here. If I take the absolute value of some number x plus 1, and when I take the absolute value of it, I want it to be negative 3. So this is asking what number has a distance of negative 3 away from 0. So one might think that, hey, well, we know that 3 has a distance of 3 and negative 3 has a distance of 3. But that's different from negative 3. There's no such thing as a distance of negative 3. So what happens if your absolute value here is equal to a negative number? It's no solutions. Okay, you cannot have an absolute value equal to a negative number, as it's there. You can't do it. There's no absolute value. You could take a calculator out, try to take the absolute value of any number you want. It will never be equal to a negative number. It's only equal to non-negative numbers, meaning 0 and positive numbers. Okay, so now that we kind of have the equations under control, let's go ahead and think about the inequalities. We have a table here, but what I want to do is I kind of want to figure some of these parts out, and then we're going to go back and fill the table. So keep this handy, and as a matter of fact, I think some of you are going to really like having the table for absolute value inequalities. But let's just go ahead and solve these problems here. Okay, so here I have 2 times the absolute value of x plus 4 minus 1 is less than 19. Now notice that this is here, it's a less than sign, it's not equal to. Okay, the idea of getting the absolute value isolated, though, still is going to hold true. So let's just take a moment and isolate the variable. So why don't you go ahead and do that as I'm doing this now. Okay, so we're just isolating the absolute value symbol here. First, I am going to add 1. Okay, and then after that, I'm going to divide by 2. So I have the absolute value of x plus 4 is less than 20. Okay, so let's think about this. I have the absolute value of x plus 4, and it's less than 20. Okay, so when I'm taking this absolute value here, and I want the absolute value I know is going to be a positive number. I know it's going to be less than 20 as well. So if we just kind of think about our number line here, and as a matter of fact, I might just sketch one down here. We can just think about this here. I know that my answer is going to be less than 20 when I graph this, right? So if I take the absolute value here of 21, when I take the absolute value of that, will that be greater than, or will that make this true? Like if this whole inside part here is 21, it would make it false, right? Because if this whole thing here is 21, when I take the absolute value of it, it's going to be 21. Well, that's not less than 20, that's greater than 20. So what about 19? What if I took this whole, and I'm not talking about the x value, I'm just talking about this whole inside the absolute value symbol. If this whole part here was 19, would that satisfy the inequality? Well, if this whole thing was 19, I would take the absolute value of 19 and get 19. And that would be less than 20. That would work. So here, I think when I'm setting this up, you're going to have two things to write again. I know that x plus 4, the inside there, needs to be less than 20. Okay, but as normal, we know that these inequalities, I mean, we're just talking about the right side of 0. What about the left side of 0? Because that's going to matter as well. So let's just kind of do the same thing. Let's just think about the number line and what would happen about the insides here. So we kind of know negative 20 is going to be important to us. So what if I have negative 21? So let's say this whole inside part here is negative 21. Well, when I take the absolute value of negative 21, that's going to be 21. So would 21 be less than 20? No, it would not. So I kind of know that my answer can't be, to the left of 21. But what about, what if the whole inside part was negative 19? Okay, so if this whole part was inside of negative 19, well, negative 19, the absolute value of that is 19. And that is less than 20. So that would work. So I do have this other side here that needs to be accounted for. And I know it's going to revolve around negative 20. But one thing we have to kind of keep or to think about here is that, yeah, when I take the absolute value of this thing, it did need to be less than 20. But what does it need to be in regard to negative 20? Well, we figured out that it couldn't be less than it, but it could be greater than it. So here, this is the part that makes it kind of tricky, is your two inequalities, like one is going to be kind of the way that you think it's going to be, but then the other one here, you do have to switch your sign and negate the number, kind of like we did before. Okay, and we're going to get a little bit more practice with this here in a moment. Okay, but, so I know that the absolute value of x plus 4 is less than 20. That means that x plus 4 needs to be less than 20, so I can satisfy this side of the inequality. But then x plus 4 needs to be greater than negative 20, so we can kind of satisfy this side of the inequality. So let's solve that and see what it looks like. It means x can be less than 16. And then when I go here, and then x also needs to be greater than negative 24. Okay, so let's go ahead and let's call this negative 24. We'll go by 4, so negative 20, negative 16, negative 12, negative 8, negative 4, 0, 4, 8, 12, 16. Okay. So this one is an inequality, so there's going to be some amount of shading here going on, so we need to think about how that's going to look. Well, first off, let's just start with this one here. So x is less than 16. So that means it's an open circle because 16 is not included. If this x value is 16, that is not going to satisfy this inequality because that is equal to 20. Okay, and it says it needs to be less than, so I'm going to have to start kind of shading this direction, right? Any of these values will work. Well, what about x is greater than negative 24? Well, I know it's open circle here on negative 24, and greater than, it's going to have me shade off to the right. Okay, so this here is what kind of inequality. So you're going to have to think back to section 1 and 2 of this chapter, but what kind of inequality is this? Where they come together, they create an island. So this is an and inequality. Meaning that for my x values to be a solution to this, it's the compound inequality. My x values need to be a part of this compound inequality where my x values have to be less than 16, and meaning both of these have to be satisfied, and it also has to be greater than negative 24. So let's go up to the table and kind of break down what we have. We have a situation like this. Okay, so the equivalent form of this is that we are going to have the opposite of c value here and the positive c value there, and it needs to have the and inequality ax plus b. Okay, the other way to look at it here is that inside part needs to be less than the positive version of the c value, and that inside part needs to be greater than the negative version of that c value I have. Okay. Then here, what our graph is going to look like, it's just going to be some number. I'm going to put numbers because they're not always c. Okay, and they're going to be open circles, and it's always going to create an island. This is always going to produce an and inequality. Okay. When the absolute value is just strictly less than some number, it's always going to be an and inequality, with our boundary numbers having an open circle because they're not included in the solution set. Okay. So I want you to go ahead and try C on your own. Hopefully you're going to kind of start to figure some things out on your own as you're working through these, okay? So pause the video now, try it. Okay, so I'm assuming that you've already done that and you're just here to check your work, okay? So the first thing you need to do is get that absolute value symbol isolated. Okay. And now what we need to think about is this is a less than sign, okay? And so when it is less than, we have to split it up. We know that 2x minus 3 has to be less than or equal to 5, okay? And that's going to, same with the number line, that's going to satisfy more of the right-hand side, knowing that that line has to be less than 5. But and 2x minus 3 needs to be greater than or equal to negative 5. Okay, so we can solve this. So we can add 3 to get 2x is less than or equal to 8, and then divide by 2 to say x needs to be less than or equal to 4. Okay, here we can add 3 to get 2x is greater than or equal to negative 2, divide by 2, x is greater than or equal to negative 1. And again, this is an and inequality. Anytime it's less than, it's going to be an and inequality. Okay, so let's go ahead and graph this. So let's say 0 is here, negative 1 would be here, 1, 2, 3, 4 would be here. Okay, now this one is slightly different than the other one. Hopefully you all pick this up on your own, in that when you have less than or equal to, the problem is going to be solved the exact same way. The only difference is, instead of a open circle, it is going to be a filled in circle. Because these boundaries are included and are part of the solution set. So x can be less than or equal to 4, okay, while also simultaneously being greater than or equal to -1. Okay, so let's go up, fill the table for less than or equal to, because it's basically the same thing. Okay, it's also going to be an and inequality. Okay, so we're going to have negative, or the opposite of c is less than or equal to ax plus b, which is less than or equal to c, the positive version of c, or kind of the way that I taught it, ax plus b is less than or equal to c, and ax plus b is greater than or equal to the opposite of c. Okay, and what's the graph look like? Well, we know it's an and inequality with some number here and maybe some number here. The only difference is it's closed circles. Everything else is essentially the same. Okay, so these will kind of help you set the problems up. Okay, really the shortcut for you all is knowing that the less than signs are going to become an and inequality. Okay, the solutions is the two boundary points kind of coming together. Okay, so I'm going to keep this handy so we can fill out the rest of the table, but let's go ahead and move on to the other examples. Okay, as you may have guessed, it's going to be greater than. Okay, so as I look at these right off the bat, there are no parts outside of the inequality for us to solve. So we can kind of just go ahead and start thinking about this all together. Okay, so again, as I look at this part here, if I want this part here, okay, so we're going to just think about the graph of this a little bit, or just kind of the basics of a graph. So as I'm looking at this inside part here, I want this inside part, when I'm taking the absolute value of it, to be greater than 3. So let's think about this. If I had this whole inside part here was equal to the number 2. Okay, so if this whole inside part here was equal to the number 2, would it satisfy this inequality? It would not, because this inside part is 2, so the absolute value is 2. If the absolute value is 2, that's not greater than 3. But what about if it was 4? What if this inside part here was equal to 4? Okay, well, if it would be equal to 4, the absolute value of that is 4. Okay, so that is going to be greater than 3, so therefore it would satisfy the inequality. So we know that our solutions, would come out here. Same thing if I think about what if that inside part was -2. Well, the absolute value of -2 is not greater than 2, because the absolute value, or not greater than 3, because the absolute value of -2 is 2. 2 is less than 3. We are looking for greater than. Okay, so what about -4? What if that outside, or the inside of the absolute value symbol was -4? Well, if it was, it would be greater than 4, and that would work, right? So we're thinking about a graph that kind of shoots out one to the right and one to the left. Okay, so what kind of graphs do that? Hopefully, thinking back to the first couple sections, we know that this is an OR inequality. Okay, this is reasonable to deduce because when we did less than, it was an and inequality. So it makes a reasonable amount of sense to think that, well, if that was an and inequality, that the opposite would be OR. And you would be correct, but this is kind of why. So let's go ahead and take a look at what we would do for this. The process ultimately ends up being the same. We're going to take this inside part here. We're going to say a half of x minus 1 is going to be greater than or equal to 3. Or a half of x minus 1, again, switch your sign, negate the number. Okay, so it's going to be less than or equal to -3. Okay, so these kind of problems get to be solved the exact same way, and whether you actually know one's and or one's or, if you solve these problems consistently of like write the first inequality kind of the way you would expect it to be, and then write the second one with this sign flipped and this number negated, you're going to kind of fall face first into the right graph as well as the right solution set without knowing whether it was and or or. Okay, so let's go ahead and add 1. So I get a half of x is greater than or equal to 4. Okay, how can I undo multiplying by a half? We can do that by multiplying by 2 to get x is greater than or equal to 8. Okay, so there's my first part. Or if I add 1, I get a half of x. It's less than or equal to negative 2. Multiply by 2. X is less than or equal to negative 4. So if this is negative 4, 2, 4, 4, 6, 8. Okay, I'm going to have bold letter or bold points on 8 and negative 4 because it's a or equal to sign, so they're included. And just like we kind of talked about above, it is reasonable to understand that they are going to be or inequalities, like the oars on a boat, where the previous ones were like the island created between them. Okay, and so you could check anything in this shaded region, like if this was 10, 12, half of 12 is 6, 6 minus 1 is 5, that is the absolute value of that would be greater than 3. And you could check that with any of these. Okay, again, kind of the same concept of inside, same sign, same number, inside, flip sign, negate number. Okay, so those are kind of just tricks to help you get to where you need to go for these types of problems. Okay. Although I would prefer that you understand kind of the basics of what I was talking about here, where, you know, we need to understand that when it's greater than, the reason why it's or is because, you know, anything in between here, when I take the absolute value of it, it's actually going to end up being less than 3, as opposed to these numbers outside, the absolute value of those numbers are going to be greater than 3. So because of that sign flippage when it comes to negative numbers and absolute values. Okay, why don't we try D on your own and then check it with me, and then we'll fill that table out. Okay, so I'm assuming you paused the video already and you're here to see how you did. Okay, so I have a fourth of x minus 2 is greater than 1, and then a fourth of x minus 2 is less than negative 1. Okay, and this is an or inequality. Okay, so I can add 2. So I get a fourth of x is greater than 3. Multiply by 4. So x is greater than 12. Okay, here I can add 2. So that means a fourth of x is less than 1 times 4 times 4. X is less than 4. Okay, so this one here, we're going to need 0 here. 2, 4, 6, 8, 10, 12. Okay, this is open circles because of this is strictly greater than. Okay, so it's not greater than or equal to, so it's exclusive. These boundary numbers are not included in the solution set. So let's go ahead and shade just like this. Okay, let's fill out that table. Okay, so here, these two, when it's greater than 1s, it's going to be an or inequality. Okay, and there's basically only one way to write this, and that's ax plus b. The inside is going to be greater than c. Or the inside ax plus b is going to be less than the opposite of what c is. Okay, and again, we're going to have some number here. Open circle. And then here, some number. I don't know what those numbers are going to be. And they're shooting out. Okay, this one's the exact same thing with or equal to signs. Okay, so the inside needs to be greater than or equal to C, or the inside is going to be less than or equal to the opposite of C. And again, same thing, the only difference is those dots are going to be filled in because those boundary numbers are going to be included in the solution set. Okay, so let's move on to the word problems. Okay, so when we are solving these problems, a lot of times tolerance problems are going to end up being absolute value inequalities, and let's kind of see why. So we have a bicycle manufacturer that uses tolerance of 0.05 millimeters for a bicycle crank assembly pin that is 8.5 millimeters wide, meaning that the pin can be 8.5 millimeters wide plus or minus like this tolerance, and it can be inside of that tolerance altogether. Okay, so we want to write an absolute value inequality that describes the acceptable width of the pin. So here, let's just take, if I say like x minus 8.5. Okay, this is, if I take that and have x be the like the actual amount of, like if I went and randomly selected one pin and that was the measure of the pin, and I take away 8.5, that is like the error that we've made. Like if it was exactly 8.5, it would be 0, meaning I made 0 error. Where if it was 9 millimeters wide, it would have an error of 0.5, and maybe that's acceptable or maybe it's not. Okay, but if I take that, and regardless of what that number is, because maybe it's short, maybe it's 8 on the dot and I get negative 0.5, we know that if I take the absolute value of it, it's going to give me a range in which is an acceptable like error or not. Okay, so for this particular problem, we're saying that it's okay if it is inside of a range. Well, what is that range? It's going to be 0.05. It says that because it has my tolerance of 0.05 millimeters. Okay, so as I'm looking at this, what kind of inequality sign? Are we saying that when I find my error, it needs to be greater than this amount, greater than or equal to, or less than or equal to? Hopefully you all are thinking to yourselves now that, it seems reasonable to assume that it needs to be at least, right? It needs to be, when I take the measurement minus what I want it to be, it needs to be 0.05 or less. So that would give us a less than or equal to. Okay, so using what we kind of know about absolute value inequalities, let's go ahead and solve this. So I know that x minus 8.5 is going to be less than or equal to 0.05, and x minus 8.5 is going to be greater than or equal to negative 0.05. Okay, so let's solve. So I add 8.5, so add 8.5. It's less than or equal to 8.55. And then here I can do the exact same thing and say x needs to be greater than or equal to 8.45. Okay, so when I graph this, for this problem, we're dealing with such small numbers. We can go ahead and say I don't need to see 0. In general, we don't have to see 0 on the word problems. It just might not be applicable. So if this is 8.5, this is 8.51, 8.52, 8.53, 8.54, or 8.55. So 8.55. 49, 48, 47, 46, 45. So 8.45. And we're saying that it needs to be greater than that 8.45, but less than that 8.55 millimeters. So here, having a tolerance of 0.05 allows me to have pins that are 8.45 millimeters all the way up to 8.55 millimeters. Okay, now this might have been something that you would have been able to tell me probably intuitively, saying, hey, if I have a tolerance, that means it can be 0.05 larger than this as well as 0.05 less than this. But the important part is being able to represent that algebraically, you know, in some sort of system that allows us to do this. Okay? So what I want you to do right now is go ahead, and I do need to see this inequality set up, as well as the graph for letter E, and then check it with me here in a moment. Okay, so another tolerance problem. So suppose we have a bicycle manufacturer uses a tolerance of 0.07 millimeters for the pins. Okay, so it's the same situation. The only difference is we're giving a little bit more leeway as far as the pins that we're creating. We're allowing them to be 0.07 larger as well as 0.07 smaller. So that means if I take the measurement of any pin and I take away the original, like our ideal measurement of 8.5, we know that that difference, we want the absolute value of it to be less than or equal to 0.07. Okay, so as I do this, I have an absolute value inequality that's less than. So that means x minus 8.5 needs to be less than or equal to 0.07, and x minus 8.5 needs to be greater than or equal to negative 0.07. Okay, so let's add 8.5 to each side, meaning x needs to be less than or equal to 8.57, and add 8.5 here, and x needs to be greater than 8.43. Okay, so let's put 8.5 here. Okay, and I'm going to go by 0.02, so this will be 8.52, 8.54, 8.56, 8.58, so this would be 8.57 here, and this would be 48, 46, 44, 42, so 43 would be here. All right, and it needs to be in between here. So for this particular tolerance level, we would allow our pins to be from 8.43 millimeters all the way to 8.57 millimeters. Okay, that is the end of this lesson and nearly the end of this chapter. So we will move on to 2.5 next time, and then that will be the end of the lesson. Otherwise, move on to the homework, and I'll see you for the next lesson.